Um, so this is a talk about game tech and research simulation platforms. So I am Seth Alter, and as Lauren said, I'm a former indie developer. I used to help organize Boston Indies. I still make my own stuff, of which you can find at subalterngames.com, but that's much more of a hobby now, or side career, somewhere between a hobby and side career. And professionally, I'm now a research software engineer at the MIT Brain and Cognitive Science Department. And I'm the lead developer of 3DWorld, which I'll be abbreviating to TDW throughout this talk, which is a joint IBM-MIT project. What I am not is a researcher. I am not a researcher. I'm a research software engineer. I work with researchers all the time. And in practice, they're somewhere between clients and collaborators. So they're either asking me to make them stuff, or they are actively contributing to the project in some way, either by coding or sometimes reluctantly doing QA. I don't actually know how most of the science works, especially in like the fine details. So if you want to know like that sort of stuff, I'm not the person to ask. And accordingly, that's not what this talk is going to be about. What I do know is the technical requirements of the research, and I have a pretty deep understanding of that at this point. So when a scientist says, I want to do X, Y, and Z, I can break that down pretty quickly into something that's can be made. So what this talk is about is the engineering and development of TDW. And I will be touching on some of the science, but only insofar as it affects design considerations of TDWs. This is much more about the nuts and bolts of the machine and less about the science. TDW uses video game technology pretty extensively, so I'm going to be talking about how that gets used in research. And I'm going to also compare it to other simulation platforms. So I've been throwing around this term research simulation platform. In fact, it's in the name of the talk. Basically, what these things are zero-player video games, and they are meant to simulate the real world. Or more specifically, they tend to zero in on a particular piece of the new world, such as the way something looks, or the way objects fall, or the way something sounds, and they try to simulate it as close as possible. And then within this virtual environment, scientists will use machine learning to solve tasks. And solving tasks can mean a number of things. You can solve tasks the way you would in a video game, which I guess there's no bullet point here, but you could solve in a video game where the AI is just trying to do something that looks plausibly like what someone would do. It's got to behave in a way that makes sense. You could solve a task the way that a person would, which is complicated to sort of break down what does it mean to solve something like a person would. You can solve a task optimally, which people often don't, or you could solve a task any way at all. And sometimes there are just problems that you can tackle with machine learning that, like, if the computer can solve in any capacity, in any direction, it's pretty neat. So to take it a step back a little further, I want to just briefly touch on what machine learning is to make sure we're all on the same page. So I'm not sure who knows this and who doesn't. The rest of the talk will be fairly technical, but I'm going to try to skew towards something that is human readable. In other words, I'm going to have a lot of code up, but you'll hopefully be able to just eyeball it and understand what's going on. So machine learning is not really learning, and machine intelligence is not really intelligent. I don't actually do the development side of machine learning, but you do need to understand this to have any sense of why I do what I do. So here's the brief rundown. Suppose you have a JPEG of a chair on your computer, and you have a text file right next to it, and the text file says this is a chair. Or in some capacity, you have a way of tagging that image and telling your computer that it's a chair. And so you do that, and the computer says, fine, it's a chair. You show it the same image, and you ask, is this a chair? And the computer says, yes, it's a chair, because it loads up the answer it gave you, and it's like, got it, I know that's a chair. You showed a picture of this chair, and you say, is that a chair? And your computer will say, I don't know, because it has no way of knowing if that's a chair or not. There's no way. Now, let's say you gave the computer a whole bunch of JPEGs of chairs, and you said, these are chairs. Computer says, fine, these are chairs. You show it a picture of this chair, and you say, is this a chair? And your computer still doesn't know. There's no way for it to know with the information at hand. It just doesn't have enough data. Now, let's say you gave it 1 million photos of chairs, and you said, all of these are chairs. And your computer says, fine, okay. Then you can show it a picture of this chair, and it will say, yes, that's a chair. So what machine learning is, in other words, is giving the computer the answers first, like a lot of answers, like 1 million answers. And if you do that and you run it through the right software, you can generate a statistical model that's sort of an understanding of the general pattern. So in this case, the computer doesn't know what a chair is in sort of it doesn't understand the phenomenon of a chair. It doesn't know that you can sit on it. It doesn't know that that it has mass. All it knows is that you have given it 1 million blobs of pixels, and it's looked at those pixels, and it has an understanding of which blobs of pixels look chair-ish and which ones don't. And that giant pile of answers is called a data set. And data sets can be most anything. They could be a folder of 1 million images of chairs. They could be cached pathfinding data. So every time that's one of your characters in your game's pathfinds, just dump the waypoints to a file. It could be a download of all the text of Reddit, and so on and so forth. And so you can take a data set and then train a model and generate behavior from that. Now, this is the part that I don't do. This is where the scientists come in, and the reasons that they will train the model and what they're trying to achieve. That's not my part of the job. But broadly speaking, what they're doing is they're going to train the model on a data set, or train the AI on a data set to get a model, and then they can use the model to generate behavior. So once you have a model of what chairs look like, the program can feasibly generate its own pictures of chairs and say, I think this is what a chair looks like. And if you give it enough pathfinding data, it could start spitting out what it thinks are good paths, because you've already given it 1 million paths and said, these are good ones. And it'll say, okay, here's what I think a good one looks like. And if you give it all Reddit, it'll start generating paragraphs of text that sound like they're from Reddit. The caveat is sort of what this thing actually is that you're giving it the answers first. So if you give it 1 million chairs and then ask, what is that, a table? It'll say, I don't know, because it has no concept of what a table is. And if you give it 1 million chairs and all those chairs are wooden chairs, you gave it 1 million wooden chairs, and you say, is this a chair? And you show it SpongeBob chair. It will say no, because as far as it knows, that's not a chair. It's never seen anything like that before. Which is all to say your AI is only as unbiased as your data set. This has profound ethical implications that are not necessarily relevant to what I'm showing, because I don't do surveillance tech, but this is the ethical issue in machine learning research and application. And it does affect what we're doing, because we're doing science. So we need to be very careful that the answers we're providing it are are not we're not skewing towards some conclusion that we want to see. The other caveats, and these are more directly pertinent to what I do, are that this process doesn't actually always save time, money, or effort. In video game development, you can achieve a lot of the same behavior by doing old style proc gen. Proc gen is less flexible, but it is much faster to make, and it is much cheaper to make, and it will look more or less the same because games, unlike science, aren't trying to replicate the real world. They're trying to look like the real world and behave like it in a way that feels believable with actually being the same thing. The other problem is that these data sets don't just grow out of the earth. Someone actually has to make them. You have to go onto the internet and get 1 million images of chairs. Now, let's say that you wanted something more complicated, like a furniture data set. Then you'd have to start doing what we call semantically tagging everything. So you get a picture and you say, this is a table, and you get another one, you say, this is a chair, and you get another one, you say, this is, anyway, you get the idea. This is an enormous effort, especially because we're talking about 1 million images. Now, if you want to have multiple data sets, or if you want to give each image multiple semantic tags, like this stacks up pretty quickly. The other problem is that so far I've only been talking about static images or static text, but anything that's moving is incredibly difficult to convert into a data set. So if you had a data set of like situations where like, can I navigate out of here? Will the tower of blocks fall? How would you even get that data? You'd have to get like 1 million videos of block towers, some of which are falling and some are not. I'm not sure what the source of that would be. You'd have to, I guess, make it your own, and that would take like 10 years. And then even then, there's no way to get the metadata from that. So there's no way to know what the mass of those objects are or how fast they're falling, unless you had like extremely constrained camera stuff and frame rate. And that just, so you can get some things from YouTube, but like there's no way of knowing any of these like metadata properties. So this is these last two points are what research simulation platforms are trying to solve. So they are a suite of tools for simulated machine learning experiments. And what we do is generate synthetic data sets quickly and easily. And synthetic data is just stuff that you can pull out of a video game engine. And then we train behavior models faster than real life. So an example of synthetic data would be 1 million images of chairs from Skyrim and Grand Theft Auto, whatever. We can generate 1 million images of those a whole lot faster than trawling Google Images or whatever else we would do. So what I do is that I give researchers the tools to generate synthetic data sets, and I give researchers tools to simulate complex behaviors within a video game engine. And typically, I do some combination of those two for any given project. And I use a common code base which is 3DWorld, that we're constantly upgrading and augmenting and fixing. And once I've achieved either or both of these bullet points, I pass the baton back to the researchers. So we use video game tech because that's actually a really good way to simulate real world phenomena. Video game engines are great for this sort of thing. Things like Unity, Unreal, they already have a physics engine. They have extremely good rendering that's meant to look like real life. And unlike something like Maya or 3DS, they're meant to be run in real time because we need this data as fast as possible, and ideally many times faster than we could gather in the real world. But the caveat is that the machine learning tools, the stuff that's actually going to be training the model or learning from the data set, those are pretty much all written in Python, such as PyTorch and TensorFlow. And video game engines, the sort that we want with good physics, high quality rendering and whatever, those aren't in Python. There is a plugin for Unity called ML Agents, but which is machine learning agents. But in practice, it's not sufficiently flexible. It does what it does very well, but the scientists that I work with, they all want to be able to mix and match from this huge universe of machine learning tools and options. And MO Agents does one thing. They want to do not necessarily everything, but they want to have all the options on the table. So there are many simulation platforms, and this is a chart from the 3DWorld website that's meant to make us look good. So you can see that we got all the checkboxes, and everyone else has some of the checkboxes. And that's that. You know, I'm saying that I'm being very flip about that, but I do work towards making this the best of the bunch, and I do actually believe that in many respects we can do things that these other projects can't do, or at least do them better. These are just some GIFs of what TDW can render. This is from a big physics project that we did. I'm going to be talking mostly about 3DWorld in this, as opposed to any of these other simulation platforms, because this is the one I make and I understand it better. But this is not necessarily a promo speech. I'm in academia, and promo and marketing is completely different than in video games anyway. So, and this is an open source project, so it doesn't matter in the same way it would with a video game. So, don't take this as a sales pitch if I'm going 90% talking about TDW and leaving these ones out in the code. I just don't know them as well. So TDW supports physics simulations, high quality image rendering. We have audio, which is very unusual for a research simulation platform. We can generate audio and process audio, and we support robotics. What we don't support is text recognition. We don't scan paragraphs or try to generate unique paragraphs. We don't do facial recognition or surveillance tech. We don't do self-driving car simulations or drone simulations or anything like that. So the way TDW is structured is that it has basically two programs that talk to each other. The simulator we call the build, and that's the Unity 3D application, and that's just a compiled executable that you start up when you want to run TDW. And then there's a controller, which is a Python script, and that contains all the instructions that you're sending to the build. And it can talk to the build, and it can talk seamlessly with any existing machine learning modules and software. And I make the build and I update the build, and then I often write controllers for people, but the controllers scripts are set up so that the researchers can write their own controllers. So they can have maximum control over their own experiments, because again, I'm not a scientist and I can't tell them how to do the science for them, and I can't necessarily predict in advance what they want at a very, very fine-grained level. So the simulation is divided into frames, physics frames, where each frame is a time step. So frame 1 is 0, and frame 2 is 0.0001 seconds, and frame 3 is 0.0002 seconds, and so on, or whatever. The time step's not that fine, but you get the idea. And then per frame, what happens is that the controller sends commands to the build, and the build processes the commands, and then it sends the controller output data. And this is all handled in a simple TCP/IP send-receive socket pattern. And if you're wondering, is it lunacy to put your entire game loop on a TCP socket, it turns out it's fine. If you run it localhost, it's extremely fast. The only thing that's slow is encoding to JPEGs from Unity. That's just a slow process because they don't do it that well. So these commands that you're sending to the build are all JSON dictionaries, which is the sort of stuff that a lot of online APIs use nowadays. And then the build deserializes JSON dictionaries, and every single dictionary has a corresponding object type in C#. And it deserializes to that object and calls the object's do method. And when all the commands are done, the build gathers up output data and returns it back to the controller. So this is an example controller that's written in Python, and I wrote it for this talk. So what it will do is generate a single image of a table with a vase on it. So if I were to run this in Python and then launch the build, which I would just double click that application, I would get this. That's all it does. It looks okay. So that's the controller, that's the build, and the text in green are the JSON dictionaries. That's the commands. So every command, like I said, corresponds to a C# object. So this on the left is set screen size, which is hopefully pretty intuitive what it's doing. It's going to set the height and within height of the screen. Those are the pixel sizes, 512 by 512. And on the right, we have the corresponding C# code. So it deserializes directly into one of these objects. We have hundreds of these commands in a vast object class hierarchy tree. And now, importantly, and this is a pretty big difference between what we do in video games, nothing happens in the build until the controller sends its the next message, the next batch of commands. So everything pauses and halts until you give new instructions. That way, the output from the build is always synced with controller input. We don't actually want Unity to interpolate anything ever between frames. We want to capture as much data as possible. And in case anyone's curious, the code to do this is in the center of this slide. You can turn off physics auto simulation in Unity and then manually step through it by feeding it a time step, or rather a delta time. So a very cool thing that ThreeDWord can do is that you can chain together a bunch of commands into a single list, because if we're advancing the simulator one frame per message, we sometimes want to have two things happen on the same frame, such as we want to add that vase and that table at exactly the same time. So we can do that by combining commands into lists and sending them all in the same frame. So everything in the blue box is actually one giant list that's all going to get sent on frame one. And if you were to crunch that down, it would look something like this: add scene, set screen size, set shadow strength, set aperture, set focus distance, and so on. And all of that gets sent in this call called self.communicate commands. And we receive a response, which is the resp value. Every command in ThreeDWord does exactly one thing, which we don't have a move an object and rotate it command. We have a move object command and we have a rotate command, and you can chain those two together in a list. These lists can get very long and they can generate arbitrarily complex behavior. It's a fairly unique approach, as far as I know, in simulation platforms. Our API has hundreds of commands and it's very granular. And it's very easy for me to add new commands because they're all sharing each other's code. So in this example, I mentioned we have this value resp here, and that is the output data. Resp is a list of byte arrays, and that can get deserialized into flat buffer objects, and flat buffer is like protobufs. If they are binary data, they're not JSON, in other words, they're not strings, because that ends up being too slow. because we're sending back images. So these are byte arrays, and you have to, in the API, explicitly state what data you want. So in this example, we are setting the pass masks, and I'll tell you what that is in just a moment. And then we request images in the send images command. We send that all to the build and the communicate call. We get a response in blue, and we loop through the response in blue. And one of the elements in that list is images, and now we have images. But we have lots of other types of metadata too, or data too, and I'll get to that. I mentioned these image passes. This is pretty foundational to how research simulation platforms work. There's the way that the computer's actually seeing things can vary a lot. So in the top left, we have the image pass, which is just the regular old render of the image. That's a PNG file. And we have the ID pass, depth pass, and normals pass. And we often want all these at once. And this is handled via a couple of shaders in Unity. The ID pass is pretty key. Whenever we create an object, we assign the object a unique color. The ID pass fills that object in with that unique color. So when we get this pass back, we can scan the image and we can get the colors in the image, and that will tell us whether the camera can see the object or not. And it can also tell us how occluded is the object, whether we would expect more pixels or if there's something in front of it, and so on. The depth pass is the distance from the camera to the pixel if you were to shoot array. And it's 24-bit data encoded into RGB channels. And it looks wacky, but I promise it's accurate. We've tested this one. That's most of what I did for the winter. I'll put it that way. And the normals pass is the vector perpendicular to the mesh face. Now, I had showed you before a example of just a static image, but we can do physics behavior because this is Unity, and this is the same simulation, but I just put the vase higher up and let it run for a bunch of communicate calls. I saved out the image and ID passes and then stitched it together with FFmpeg. But we don't just have images. We can have all sorts of data that we return. So in this example, we are requesting some physics metadata. We want to know the velocity and the position of each object at any given frame. And so the input looks a little like that, and the output looks like that. We get the position and the velocity of each object per frame. We can, and what can we do with that? We can do what you would do normally in a video game. Now we know the position of the object, so we can direct a robot towards that point, or we can guess where the object's going to be next given the velocity of it, or we can dump all that information into a data set and train on it later. But we can do simple conditional loops where if the object's at close to a position, then gets some commands, and if it's not, get different commands, and send those to the build and get a response. I want to briefly touch on the documentation of TDW, mostly because I personally am very proud of it. I've worked very hard to extensively document this whole project. Every aspect of the API is fully documented and is guaranteed to be up to date. And we also have about 30, I put down 30, but I think there's like 40 how-to articles and tutorials and lots of example controllers that you can look at to get a sense of how to structure your own project. The command API documentation is actually generated automatically from code comments in the C# code, and then that is turned into GitHub-friendly markdown pages. So it pulls the code comments out, and it also creates examples of the JSON dictionaries that you would be using in Python. So you can copy paste those back into your code. So using TDW, we can generate data sets of images, such as the image and ID passes. We can dump physics data to the disk. We can generate audio and save WAV files to the disks. And we can do any combination of those all at once, or other things too. We have lots and lots of different types of output data. The main advantages, therefore, of TDW to other simulation platforms, one is the arbitrary complexity that I've already mentioned. Two is that we maximize Python side functionality. And what I mean by that is that actually the Unity side is like fairly light. It's going to be doing a lot of the automated stuff, like once the object starts falling, the physics engine will kick in and it will do what it's going to do. And likewise, the rendering is all handled for us for the most part. But the guts of it, like navigation, navigation is handled on the Python side. That's up to the researchers to define what navigation means. And much of the math is handled on the Python side as much as possible. If it's possible to let the researchers have a go at it, we let them do it. TDW also doesn't have a single metaphor, so a lot of these research simulation platforms have a metaphor, which we would call in video game design sort of like the hook of the whole project. So AI to Thor, for example, is all robotics, and it's always in an interior environment. So it's a robot moving around a room, and other projects have similar constraints of what the levels are. We don't have such constraints. We don't even have a clearly defined definition of what a level would mean in TDW. You do have to have like a background scene, but we can spawn empty scenes. So it's not the same thing. We can do outdoor environments. We can do indoor rooms. We can do robotics. We can turn physics off altogether. We also have generally superior rendering to other simulation platforms. We have some features that no one else has. We can do in a limited capacity fluid simulations, for example, and we can generate audio from physics, which actually video games can't do yet. And it's very well documented, and I have looked through. It's probably the best documented. I'll put it that way. I've done my best with the other projects. The disadvantages of TDW, one is that we are using PhysX, which is Unity's physics engine, and PhysX is not great. Any of the loopy problems you've seen in a Unity game with physics, they happen here, but now we're trying to do science with it. PhysX is also not deterministic, and that means that if I run the simulation and you run the exact same controller as I do, we might get different results if we're using different computers, which makes it really difficult to say for sure if we can reproduce scientific results. TDW's dev team is very small. It's just me and my boss, and that means that we can't necessarily develop as fast or respond to bugs as fast as other teams. We're a very new platform, so a lot of ongoing research. It would be a very hard sell to tell them to switch to a new platform. And the granularity of the API, which I've been telling you all about how great that is actually in practice very hard to use, because out of the box, you're not going to get complex behavior from TDW. You're sort of getting the Lego pieces to build a robot arm, but not the robot arm. So I've been working in the winter and spring to solve this last point, the granular API issue that's been causing people headaches. And we recently released what we're calling the Magnebot API, which is a high-level pseudo-robotics API. And I say pseudo-robotics because it behaves like a robot, except you can see that the way it's holding that little vase there is physically impossible. It's sort of what we call magnetically grasping it, but it's not a robot that it could exist in real life. It behaves like a robot would. The Magnebot API uses the TDW and the TDW command API as the backend. So this is entirely reliant on TDW plus a couple other Python modules. And it combines our commands into simple function calls that you would want to use in almost any scenario to generate complex behavior. So I do want to back up for a sec. We do, in fact, support robotics. TDW includes real-world robots such as UR3, Sawyer, Baxter, and so on. And we actually have the ability for anyone to import a URDF robot definition file into TDW, and it will just work. And you can, so this is a GIF of one of these robots in TDW. It's the way it's controlled is that you send commands to set target angles per joint, and then you wait until the joints are at that target position. But we don't have a high-level API for this, so you have to do a per joint setup. So this GIF was generated with, well, this is actually only part of the code. It keeps going well off this slide. So it's involved with how to set up a robot like this. Now the Magnebot API, on the other hand, sort of collapses all this stuff into common behavior, and it looks like this. So we have a much more intuitively named commands, such as init scene, which initializes the scene, move by distance of 1 meter, and turn by an angle 45 degrees, and it generates this GIF over here. Magnebot, as I said, uses TDW, and everything it's doing, it would use some miscellaneous Python modules to decide what the next set of commands should be. But at the bottom core of it, it's going to assemble instructions into a format that TDW understands, which is commands. Send those commands to the build and get a response just like anything else. So what I'm showing you here is a snippet of the move by function, which is going to move it by a given distance. And we can see here some of that green text, and that is a TDW command called set revolute target, which will set a revolute joint, and that's like your elbow or a car wheel, so it's revolving on a single axis. And this is how the wheels spin. We tell if we want the wheels to spin, we'll say to all the wheels, set revolute target to 720 degrees, and then they'll revolve 720 degrees. Or rather, they'll start to turn that way. We're setting the target, and then we have to wait till they finish turning. And we do it that way because we want to detect collisions along the way and maybe change the Magnebot's behavior if it hits anything, for example. All of these commands get sent in self-doc to communicate like any other TDW call. I've been alluding to how we want to like shove everything onto the Python side as much as possible, and the way we handle arm articulation, the way the arms bend, is a pretty good example. The arm bending is, of course, in Unity. But the way we calculate where the arms ought to go is in Python, which is a pretty weird approach. I've set things up so that the inverse kinematics calculator, which is in Python, for those who are not familiar, inverse kinematics is basically like if you personally want to reach for a cup on your desk, you could calculate the way that your shoulder and your elbow is, like, given the length of your joints, the way that your shoulder bends, the way your elbow bends, and so on, you can figure out mathematically where your hand ought to end up. So that solver we do on the Python side. So on this left image, you can see we have a function called reach for, and that's reaching for a target position. And in the middle image, we have a plot that's generated in Python. This is in debug mode. We don't generate plots when this thing's actually running for real. And then the behaviors on the side in Unity. And the advantage to this is, once again, we have maximum control over the simulation when it's on the Python side. And the Python IK solver is much more lightweight than anything that's in Unity. Everything that does this sort of stuff is tied to animation or tied to some larger scheme, and we don't actually want that. That's all to say that Magnebot's behavior is purely physics, or nearly purely physics driven. The motions that it's doing are not animated. They don't use animations. They don't use prearranged behaviors. This is all rigid body physics. Those joints are moving via a Unity component called articulation body, which is new to Unity 2020, I think. And basically, they're hinges, except they don't suck. The only thing that I guess is not truly physics driven is the way grasping works. And when the Magnebot grasps the object, it temporarily destroys its rigid body, which is controlling its physics state. So it's not that the magnet is attached to the object so much as that object becomes part of the magnet temporarily. And that's how we handle object pickup to make sure that it's the physics simulation doesn't glitch out on us like Unity is wont to do. But other than that, everything is responding to the physics state. So you can use Magnebot to generate some very complex behavior. So we just launched what we call the transport challenge. And in the transport challenge, there's a bunch of small objects in a house, and the Magnebot needs to transport them from one room to the other. But it has the option of learning how to use, of learning how to put objects in a container. And if it does that, it's going to be able to transport to the objects a lot faster than if it was doing them one at a time. So basically, we're going to, the challenge is to teach the Magnebot navigation, which is sort of the easier part, and then basic tool usage to efficiently transport objects, which is sort of a novel thing. And that just launched, and that is a challenge because you can write your controller and submit your results, and if you do it the best, then something good happens. Future development for TDW, we're always developing more stuff. One of the neat things about this job, working with academics, is that there are endless numbers of novel puzzles that sort of by definition no one's thought of before. So we're always tackling like really out of left field things. So there'll always be more functionality that I can add on. Right now, in the immediate future, the stuff we're most focused on are super high level Magnebot APIs like the transport challenge, which is sits on top of Magnebot, which sits on top of TDW. So we're going to be making more of those. We got another one in the works. I can't say more about it yet. And actually, we have two of them in the works. God. And I have two of them in the works. We hope to improve the physics simulation and maybe one day stop using physics and switch over to something that behaves itself more reliably. So if you want to get TDW, you can, because all this stuff is open source. TDW is an open source repo that's got all the Python code. The build you can download for free, the C# stuff, but you can't download the C# code. That's still closed source because we use a couple modules that we can't open source. You can get the Magnebot module also and the transport channel stuff. All this is open source, and you could play around with it as you please. You need Windows, OS X, or Linux. We always test on Ubuntu. and you do need a GPU to do all this rendering stuff. And I encourage all of you to check this out. I personally think it would be really neat if people were using research simulation platforms for non-research purposes, like making weird video games and using this as the game engine. And that's that. And I guess I want to open it up for some questions.
This is great, Seth. Sorry, I think did I just jump on somebody?
Nope, all you.
Okay, cool. So Seth, I love this. This is awesome, and it's a really great, like very cool transition from your like, I don't know, really interesting, like kind of mechanics driven, you know, like weird, interesting games with a lot of systems going on to, you know, this research platform that is about, you know, kind of intense mechanics driven performance. So very, very good stuff. What's the I don't know what I don't know if you can tell us, but what's the most unusual simulation that you've seen in the platform that we wouldn't necessarily expect?
The most unusual. Oh, there's so many weird ones. Think. Oh, I know which one. Let me. Let me see if I can find it. I might have some saved GIFs somewhere. Oh God. If I don't, that's bad on me. They're so weird. So we did this thing where oh God, what was even the point of this? They had we have a bunch of mocap animations, and we had a bunch of models. We have like 5 models and like 19 mocap animations. So we generated a data set from that matrix in a bunch of different so like a 9 times 15 times whatever, however many scenes we put them in. So like 10 scenes. So like it's like a 5,000 video matrix of just the most uncanny valley like animations you've ever seen in your life, to see if the computer could guess in advance what the motion is, and the answer is no, because they're really uncanny. So like we had like, you know, we had an animation of a guy climbing up the ladder, but no ladder. So it's just the guy climbing up into space in this like hyper realistic looking environment. And we asked the computer, can it guess that it's climbing up the ladder? And the answer is no.
That's fantastic.
Good to hear from you, by the way.
Oh yeah, you too. You too.
Hey Seth, so actually you had answered one of my questions that I was going to ask, whether the wheels were using physics on the robot to push the robot around rather than animated. When you're doing that, are there any sort of like friction coefficients or anything you're using for the floor surface? Because obviously those vary with different floor surfaces and stuff like that.
But we don't. You can modify those in TDW, but we tend not to. We tend to just stick with the defaults. Friction coefficients in Unity, you can assign them, but they don't actually directly map back to the way friction coefficients actually work. So like setting low friction values is not quite the same thing as like creating the ice level. But we do play with them. I guess you can't set the wheel friction values, but I could write a command in 10 minutes that would let you do that. For other objects in the scene, like if you want to like drop a cube on a ramp and let it slide down, there's actually a couple experiments that just did that, just endlessly dropping cubes on ramps and adjusting friction coefficients and getting different results.
Oh, that's cool. That's cool. Thank you. No, that answers my question.
You're welcome.
Awesome talk. I have a question myself. So you mentioned earlier that using Unity, physics can present some occasional issues with non-determinate behavior. I'm curious, how does that affect, I guess, what you determine to be a success in a simulation? And I guess as a second side question, what made you settle on Unity as a game engine platform as opposed to some other game engine?
Yeah, those are two different questions. I'll answer that question first. By the time I was hired, it was already Unity, and I know Unity. I already knew it. So I was in favor of this and continue to be in favor of it because I don't know Unreal, and I want to do what I'm very good at. Physics is a weird choice, but there are plugins for Unity that we could switch over to. I think. Sorry, what was your first question?
So I was just wondering, because you mentioned that physics is non-determinate, and so therefore can have lead to some issues in terms of like replicability of simulations. I'm curious then, like, what do you consider like a successful replication of a simulation? Like, how do you determine that?
Yeah, so it's difficult to replicate the exact same run of any given simulation, but in the context of, so if the goal is to replicate behavior, that's actually quite difficult, if not impossible, and that's like a very strange problem that we hit from time to time. But if you're training a machine learning model, it doesn't matter because the whole point of it is that you're training it to handle situations that it hasn't hit before. So if you train it and I train it and our behavior is slightly different, the model is still basically the same. And if you present it with a new challenge and I present it with a new challenge, it's gonna figure it out. It doesn't matter that much. In fact, the variance is probably beneficial to the model because it's going to see different things.
Gotcha. Thanks. That's really cool.
That's my like rosy-eyed best case scenario answer. Yeah, in practice, sometimes we do need it to do the exact same thing. Like if those videos that you were watching, if I want to generate demo footage, if someone sends me a controller to render a video, I might not get the same behavior and I might get a different video than what they were structuring.
So if we were interested in kind of downloading these and trying them out, is the documentation there on the GitHub, or is it okay?
Yeah, so if you go to the README, it'll be in big H4 header.
Yeah.
This is the getting started guide. Click this.
Cool, great. Yeah, I'll give it a try. I have one tiny dumb question. You mentioned at one point that with the Magnebot simulation, when you pick up an object, it essentially destroys the rigid body. Couldn't you just set it to kinematic for the duration of the?
Nope. Nope, super duper can't. Nope, super can't.
Really?
It really needs to be in the exact same place as that magnet, and it really can't like interact in odd ways with other objects.
Gotcha. So you remove the component, and then when you set it down, it creates the component.
I remove the component and I set the mass of the magnet. I increase the mass of the magnet and set its center of mass to be the average of the position, so that it's as far as Unity is concerned, it's the exact same thing.
Right. Got it.
So you can't like deactivate the component. You have to destroy it.
You can't deactivate rigid bodies. Isn't that the darndest thing?
Right. Yeah. Isn't that weird? It's one of the few components that you can't just deactivate.
Yeah, can't do it. You have to just wipe it. Previously, I was using a fixed joint component to attach it to the magnet, but that doesn't work. It's actually very glitchy, and there's weird rubber banding effects. Yeah, that's what I said.
Yeah, even though it's supposed to be fixed. Wow.
Yeah, really isn't. So like if the Magnebot wanted to hand an object off to another Magnebot, it really can't, because that object doesn't exist temporarily. But otherwise, this works just fine.
Huh. That's wild.
It also can't lose its grip on something. That's also an impossible behavior. And
Yeah.
for the purposes of science, sometimes it would be nice if it could lose its grip on especially heavy objects, but it can't.
Right. Got it.
I have kind of a weird question, and that is, since you're not really using like computer vision for the system to scan images, right?
By scanning images.
Well, for inputting it, so what my question is, if you're not using some sort of computer vision where the system is using a camera to look at various images or things in the real world, if you are, if you were doing that,
We could.
sure. So like potentially you could, but in the way that you're inputting, for instance, like images of chairs and everything, since those images are made out of pixels, how does the computer know? How does the system know that, like, which group of pixels is actually the image, because it's all made up of little tiny things? Like how does it know that, like, this is I should look at this whole thing at this scale, even though I understand like each single pixel individually?
I can't answer that. That's the part I don't know.
Okay.
Not at the level I think you wanted answered. I just don't know. I don't know the full answer to that. All I can say is that if you give it 1,000,000 chairs, 1,000,000 is a very big number, and it will figure it out.
Okay. Yeah. And this is more like even an image of one chair. Like, how does it know that? Like,
It just knows. It knows it's.
But I guess
It knows if you give it one chair, it knows it's one chair because you've semantically tagged that JPEG and you said that's a chair. And if you show it another chair, like you saved it chair.jpg, so now it knows it's a chair, and it only knows what these things are if you semantically tag the image and say this is an image of a chair.
Okay. Yeah. Because it gets just that somehow it is scanning, understanding the image, but
the other thing,
the pixels, like our eyes see the pixels all together. Because
right. The other thing that that machine learning people will do is they'll draw a bounding box around a slice of the image. So they'll draw literally a red box in MS Paint around the chair that's in the image, and they'll say that part of the image, that's the chair, and they'll do that for 1,000,000 images, and that tends to work pretty well.
Okay, gotcha. Okay.
We don't need to do that because we have the we have segmentation. We have the ID pass. We have segmentation colors. So the equivalent to bounding boxes in our situation is this.
I see. Okay. Yep. Got it. Okay. Thank you.
Welcome.
I'm interested to know. So you mentioned before this job, you were an indie game developer and have worked on a number of projects. And I'm curious, outside of just sort of like background experience with Unity, has the work you've done on past games influenced the way that you approach like the challenges at this job? And
yeah, sure has.
and like in what ways?
I think the main thing is that my first project, Neocolonialism, was written in Python, and it had a whole multiplayer system that was built on low-level sockets. This was a mistake, and for all the students in the room, do not make a server using TCP sockets as your first project ever. That was horrendous, and I learned a lot, but truly difficult and much harder than it needed to be. And my second project was in Unity, which was No Pineapple Left Behind. So there was an ad, MIT put out an ad for someone who knows Python TCP sockets, and Unity C#? And I said, yes, I do. I do in fact know both of those things. So I had a pretty clear understanding of how to get the two to talk to each other from the get-go. I mean, I think that's the main thing. I was being able to hold both programs in my head at the same time. It's been very helpful. And I guess the other thing is I have an understanding of when to use C# for something and when to use Python for something, and what the advantages are one over the other.
That makes sense. Thanks.
Okay, sorry. I do have one kind of semi-important question.
Yeah.
We're going to have, so there will be self-driving cars all over the world. If we equip them with abilities to image other things around them, more stuff than they need to know in terms of like navigating the world safely, hopefully, and stuff like that. If they compile all that information, because they'll be all over the place, will that make them smarter, and will they take over?
So I'm going to preface by saying that I don't do self-driving cars, and I'm not a machine learning ethicist. So this is outside of my expertise. I'll say that self-driving cars are never going to take over. It's not going to happen. B, we can't give them all the information. We will give them a data set, and they'll know what they know and they're trained how they're trained. And they'll never be intelligent. They'll only know the answers we gave them. If we teach them to avoid pedestrians at all costs, and that's what they'll do. And if we teach them that sometimes they're going to be in the trolley problem, they have to make a call. The call will tell them what call to make, and they'll do it. But they can't innovate by themselves, and they never will be able to.
Sure. I'm actually thinking of the cars being a mechanism for getting data sets of lots of different things around them, how humans behave, how people move, other stuff, not just having to do with just them driving around, because they're mobile, because they go around, they go everywhere. And it's gathering data.
Someone might do that, but I personally am strongly not in favor of gathering data on people without their explicit permission.
Yeah, and neither am I. But it occurred to me.
I'm sure someone will make the attempt, though.
I'm sure they will. We're doomed. We're screwed.
It's super interesting though that you brought that up, though, because actually just today I was talking with a couple of other people actually at MIT about like one of the challenges with self-driving cars and the fact that like it may have to choose between like in the case, like does it crash into does it crash to save a couple of pedestrians, or does it crash to save the driver? And I think there's at least one company that actually did put like some sort of hard-coded thing, or at least admitted to it, that they're going to save the driver.
Yeah, I mean, they have to choose something. Yeah, I mean, they have to train a model. They have to choose which data they're giving it, and how they're rewarding the model as they train it. They can't just tell it to make up its mind. That's not how machine learning works. I'll also say that like if we truly want safe self-driving cars, we should put them on rails, in which case what we're actually talking about is trains, and trains are very reliable and safe, and we should probably just do that.
Didn't we already have like technically autonomously moving transportation and like horses like behave by themselves and they like navigate on their own?
Sure, but like if we just threw $1 billion at the MBTA, it would basically do everything more reliably and faster that we're trying to do with self-driving cars.
But you think for like safety reasons that a car would like listen to someone telling them to stop, like someone could command a horse to stop?
It depends. I can't answer that.
All right. Well, if there are no other questions, then I think we can call it there for the evening. Seth, thanks so much for coming in. I guess I should ask
Yeah, this is great.
before we break. Do you have any like pluggables or things that we should keep an eye on for the future? Projects, social media, anything that you'd like the world to know?
I mean, these are the links for what I was talking. Thanks for listening.